Hello everyone, and welcome to our project, our last Intro to AI project, in which we are actually tackling the convolutional neural network for image objects classification. As you can see, we are using Google Colab which makes life easier for us as teammates. There's three of us, and it helps us collaborate out of the box. Um, and of course, we're using Python for this. As you can see, we're starting by. Oh, first of all, before I get to the code, just a little overview on what we're doing. We're trying three different architectures, so three different models, and then um, we are we try to fine tune the third model using different values for hyperparameters, and then we just compared everything and had some results towards the end. So this video is just a demo for all of this. So first of all, we are importing our necessary imports, loading our data from a remote server, which is very convenient here. Then we do some printing, and we create 10 random images from different data sets of the CIFAR 10. Yeah, and now we move to our first model. This is where the fun begins. Um, so first of all, as you can see, we have the conv2D, which are the convolutional layers, along with the max Pauling 2D. We have three of those layers with two max Pauling layers as well, and then we use the flattened layer, which is integrated to transform the multi-dimensional output into a single-dimensional vector, preparing it to the dense layers. Right. Uh, yeah, which by itself is containing 10 units, and it doesn't include an activation function. It's tailored for simply a 10 class classification problem, which is the one that we're talking about here. Good. So here we're just using model summary to get the summary of our model. Um, and yeah, so showing the output shape and total parameters and all of that. Of course, after that we just compile using the Adam optimizer, and we're just summarizing here again, and then we train our model here. As you can see, we tried 29 epochs. Uh, we tried first 25, and we saw that the accuracy kept improving, so we tried to push it a bit further. So we tried 35, and then we noticed that the accuracy after 29 it starts decreasing, and then decreasing again, and so we just stopped at 29 because this is the best number of epochs we found. And these were the final results. As you can see, the accuracy um, kept increasing here, and the loss kept decreasing. So after that, we decided to bring a different layer of complexity and move to the second model, um, uh, with increased depth and depth. And in this one, we just again using the convolutional and max Pauling, as you can see, but we added the dropout function, and with different values 0.2, 0.3, 0.4, with different layers, so we can see how it goes. And we run it again um, here because we just tried to run it a second time, but in the report you will see that it's uh, the final result at 29. And we got our results again for the second model. And then for the third model, um, we tried to make it more regularized using dynamic learning rate adjustments. So basically, we just tried to change uh, the learning rate dynamically, so it's more adaptive, and it's more automated and dynamic. And yeah, we're still using the convolutional at base, and we're adding also some max Pauling, of course. And after that, like once we got the model summary and we trained it, so here we are training the model again. We also use the early stopping feature. Then we tried to plot the results of this model. So we got the model accuracy and the model loss. And that's what we can see here. We will compare it after to the fine-tuned model because you will see how those graphs are different. Now, before moving to the next part, we noticed that we were using the CPU here, which was taking a lot of time. Like for example, the epochs here, it took about 2 hours to finish all these 29 epochs for the third model. And so we looked it up and found that we could use GPU here. So we started a new project and just imported again everything, and it was much faster from hours to minutes. And yeah, so we just re-imported everything and retrained the Model 3. Yeah, and so this is where we started fine-tuning the third models. So we tried changing different values of hyperparameters using this grid. So we tried different learning rates, different batch sizes, different epochs, um, dropout rates, and optimizers. And yeah, we again trained the models for every, as you can see. This is the first one, the second one, the third one, the fourth one, the fifth. Every one of them is random because it was a bit much to go through every one of them. We just picked random 5. And as you can see from the graph, the purple one, which is the batch size 32, the parameter 0.4, epochs 15, learning rate 0.001, and optimizer add-on, it's shows that it has the highest. Oh, sorry. It has the highest validation accuracy overall compared to all the other models. Well, all the other ones are pretty much well and a bit similar when like between 2.5 and 7.5 epochs, and then as the number of epochs increases, the difference between all of them changes. Uh, so after that, we simply again took the best one, in this case the purple one, and we tried to create a new model for it, taking these parameters, these hyperparameters. And so we created a new model, we called it model best. And after taking this new model, we again compiled it and plotted all the, well, trained it, and then we plotted the model accuracy and the model loss. This is the one that I want to tell you that we compared to the previous one, which is the Model 3 one. So in this in this one, this is the graphs for the Model 3, and these are the ones for the fine-tuned Model 3. And so as you can see here in the comparison, the fine-tuned model, it shows that there is a narrower, like a smaller gap between the training and validation metrics. Like unlike this one, it's narrow but not as narrow as this one. Which this we concluded that it's a positive indication that there is reduced overfitting here and better model generalization. So meaning that this model, or that the fine-tuned model, will achieve better better accuracy when trained on newer data, unlike this one, which may too overfitted, maybe not that much, but like it's this one is better. The fine-tuned one will deal best with new data. And yeah, and after that, the final step was simply creating the confusion matrix, and we did that, as you can see, for both Model 3 and the fine-tuned models to compare between the true labels and the predicted labels. This project made us learn a lot about machine learning, and specifically like how to apply it in this case in image processing and image classification. And thank you for watching.